Right now, the brains of most people over 50 are physically getting smaller. Not metaphorically, not gradually in some distant future. Measurably, structurally, and in many cases, far faster than biology alone would ever cause. Because something specific is accelerating the process, and most people have no idea it is happening. Most people assume that brain shrinkage is something that happens to other people. Older people, people with dementia, people who are clearly unwell. They assume that as long as they can hold a conversation, remember where they parked, and follow the news, their brain is essentially fine. But neuroscience has now documented something deeply important that changes that assumption completely. Brain shrinkage, the actual physical loss of brain volume, begins in most people somewhere in their late 40s or early 50s, progresses through every decade that follows, and in a very significant number of people is being dramatically accelerated by causes that have nothing to do with age itself. Causes that are sitting inside daily habits, inside medical conditions that are going untreated, and inside biological processes that are running silently in the background of everyday life. The brain that most people assume is aging normally is, in many cases, aging dangerously fast. And the difference between those two things is not fate, it is information. Brain shrinkage is not just aging. In most people, it is being silently accelerated by causes that are specific, identifiable, and in many cases, directly modifiable. Think about the small things that have been showing up more often in the last few years. A name that used to come instantly now takes a moment too long to arrive. A task you have done 100 times requires a beat of extra concentration. A conversation moves slightly faster than it used to, and you find yourself working a little harder to keep up. A word sits on the tip of the tongue and will not come. Most people over 50 notice these things, feel a quiet unease about them, and then tell themselves it is just age and move on. But what if those moments are not random? What if they are the earliest surface signals of something happening much deeper, inside the actual physical structure of the brain, that deserves to be understood and addressed rather than accepted and ignored? I am Dr. Claire Carter. Everything in today's video is grounded in real research. My goal is not to alarm you. It is to give you the clearest, most honest picture of what is actually happening inside the aging brain, and what you can genuinely do about it. Here is what we are going to cover. The brain loses volume over time through several interconnected processes. Neurons die and are not fully replaced. Synaptic connections weaken and shrink. White matter pathways degrade, and the fluid-filled spaces inside the brain expand as tissue is lost. What we are going to look at today are the most dangerous, specific causes that research has identified as accelerators of this process after 50. The things that make brain shrinkage happen faster, hit harder, and produce consequences earlier than biology alone would ever produce. Each cause has a clear mechanism. Each one is identifiable. And understanding them is the foundation of doing something about them. By the end of this video, you will have a clear, specific understanding of what is most aggressively attacking brain volume after 50. Not vague warnings about lifestyle, but a precise picture of the biological mechanisms involved. That knowledge changes how you think about your health decisions in a way that stays with you permanently. This video is for educational purposes only and is not a substitute for personal medical advice from your own doctor. If you have concerns about your memory or cognitive health, please speak with your healthcare provider for guidance specific to your situation. Number 1. Chronic high blood pressure and its direct attack on brain tissue. The single most well-documented and most dangerous accelerator of brain shrinkage after 50 is something that affects a very large proportion of adults in this age group and is present in millions of people who either do not know they have it or are not managing it adequately. It is chronic high blood pressure, hypertension, and its relationship to brain shrinkage is so direct, so consistent, and so well established in research that neurologists now consider uncontrolled blood pressure one of the most significant modifiable risk factors for accelerated brain aging and dementia that exists. To understand why high blood pressure shrinks the brain, we need to look at what the brain's blood supply actually does. The brain is fed by an extraordinarily dense network of blood vessels, large arteries that branch into progressively smaller vessels, eventually becoming tiny capillaries that deliver oxygen and nutrients directly to individual neurons and their supporting cells. This network accounts for roughly 20% of the body's total cardiac output at rest, an enormous share for an organ that represents only about 2% of body weight. Every neuron in the brain is metabolically active and completely dependent on a continuous, precisely regulated supply of blood. When that supply is disrupted, even subtly and temporarily, neurons suffer. When that disruption is chronic and ongoing, neurons die. Chronic high blood pressure damages the brain's blood supply through three distinct and cumulative mechanisms. The first is direct damage to the arterial walls. Blood vessels, like all living tissue, are not simply passive tubes. They are active, responsive structures lined with endothelial cells that regulate blood flow, prevent clotting, and maintain the integrity of the vessel wall. When blood pressure is chronically elevated, those vessel walls are subjected to constant mechanical stress, a continuous hammering pressure that damages the endothelial lining over time. The body responds to this damage by thickening and stiffening the vessel walls, a process called arteriosclerosis, which reduces their flexibility and their ability to regulate blood flow to the brain in response to changing demands. Blood vessels that should dilate when the brain needs more blood during cognitive activity become less capable of doing so. The brain begins to receive less blood than it needs, particularly during moments of higher demand. The second mechanism is small vessel disease. The tiny blood vessels deep in the brain's white matter, the regions where nerve fibers connect different brain areas to each other, are particularly vulnerable to high blood pressure damage because they lack the protective structural layers of larger arteries. When these small vessels are damaged, small areas of the white matter lose adequate blood supply and begin to die. These are called white matter hyperintensities, or leukoariosis. They appear on brain MRI scans as bright white spots and are a direct marker of accumulated small vessel damage. They are found in a large proportion of adults over 60 with a history of high blood pressure, and their extent correlates directly with cognitive performance, particularly in processing speed, attention, and executive function. The more white matter damage, the slower the cognitive processing, the poorer the working memory, and the more significant the overall brain shrinkage. The third mechanism is the silent stroke. When a small blood vessel in the brain becomes completely occluded, blocked by the combination of arterial damage, inflammation, and clotting that chronic hypertension promotes, a tiny area of brain tissue dies from lack of blood supply. These events are called lacunar infarcts, or silent cerebral infarcts, because they are too small to produce the sudden, obvious symptoms of a major stroke. The person experiences nothing noticeable. There is no facial drooping, no arm weakness, no speech difficulty. But a small piece of brain tissue is gone. And when these silent events accumulate over years, as they do in people with poorly controlled blood pressure, the cumulative loss of brain tissue becomes significant, measurable, and directly responsible for the cognitive decline that follows. The hippocampus is among the brain structures most vulnerable to hypertension-related damage. Research tracking brain volume changes over time has shown that people with a history of high blood pressure have significantly smaller hippocampal volumes than age-matched people with normal blood pressure, and that this difference grows larger with every decade of uncontrolled hypertension. The hippocampus is the brain's primary memory-forming structure. Its shrinkage is one of the earliest and most consistent findings in the development of Alzheimer's disease. And hypertension accelerates that shrinkage directly and measurably. Research has shown that effective blood pressure management, even when started in midlife, significantly slows the rate of brain volume loss and reduces white matter damage over time compared to those with uncontrolled hypertension. The brain responds to better blood pressure, and that response is measurable on imaging. Number 2, chronic stress and cortisol's direct neurotoxic effect. The second cause of accelerated brain shrinkage is one that most people know is bad for them in a general sense, but have never understood in the specific, structural, physical way that makes it genuinely alarming. Chronic psychological stress, the persistent, unrelenting kind that runs for months and years rather than resolving naturally, causes the brain to physically shrink in specific, identifiable regions through the neurotoxic action of its primary hormonal mediator, Cortisol. Cortisol is released by the adrenal glands in response to stress and serves critical functions in short-term threat management. It sharpens alertness, mobilizes energy, suppresses non-essential functions like digestion and immune activity, and prepares the body to respond to the immediate challenge. In short bursts, cortisol is protective and appropriate. But the human stress response was designed for acute, resolvable threats, not for the chronic, unrelenting stressors of financial pressure, relationship difficulties, caregiving demands, health anxiety, and the accumulated weight of unresolved problems that many people over 50 carry continuously for years. When cortisol is elevated chronically, not in brief spikes, but as a persistent elevation that runs through days and weeks and months, it becomes directly toxic to the brain. The hippocampus is the primary target. It is densely packed with cortisol receptors, more than almost any other brain structure, because in acute stress situations, it plays a critical role in contextualizing and encoding the stressful experience. But those same receptors that make the hippocampus useful in acute stress make it uniquely vulnerable in chronic stress. Sustained high cortisol causes hippocampal neurons to retract their dendrites, the branching extensions through which neurons communicate with each other. It suppresses neurogenesis, the birth of new neurons, in the hippocampal region. It promotes the death of existing neurons through a process called excitotoxicity, where chronic cortisol exposure leads to excessive activation of certain receptors that ultimately kills the cells. And the structural result of all of this is measurable, documented hippocampal shrinkage that correlates directly with both cortisol levels and cognitive performance. Research using brain imaging has consistently shown smaller hippocampal volumes in people with histories of chronic stress, untreated anxiety disorders, and major depression compared to age-matched people without those histories. The shrinkage is not trivial. In some studies, hippocampal volume differences of 10 to 15% have been documented between chronically stressed and non-stressed adults of the same age. And since hippocampal volume is directly linked to the ability to form new memories, to navigate spatial environments, and to learn new information, this shrinkage translates into exactly the kinds of cognitive difficulties that people over 50 most commonly report. The prefrontal cortex, the region responsible for planning, decision-making, impulse control, and executive function, is the second major target of chronic cortisol damage. Research has shown that chronic stress reduces the density of synaptic connections in the prefrontal cortex and causes measurable volume loss over time. This prefrontal shrinkage produces the cognitive signature that many chronically stressed adults recognize in themselves: difficulty making decisions, mental rigidity, reduced ability to think flexibly and creatively, increased impulsivity, and a narrowing of the mental bandwidth available for complex thought. Depression, which affects a very significant proportion of adults over 50 and is dramatically undertreated in this age group, compounds the cortisol damage through an additional mechanism. Depression is associated with reduced levels of brain-derived neurotrophic factor, the brain's primary growth and maintenance protein. Without adequate BDNF, the brain loses its capacity for neuroplasticity, the ability to form new connections, adapt to new demands, and compensate for age-related changes. Chronic stress depletes BDNF. Depression depletes BDNF. And the combination of the two, which frequently coexist, creates a brain environment in which shrinkage accelerates and cognitive resilience diminishes with each passing year. Some people are thinking, stress is just part of life after 50. What am I supposed to do about it? The research is clear that it is not the presence of stress that determines brain damage, but the body's prolonged cortisol response to it. And that response is genuinely modifiable through specific, well-studied interventions. Managing the cortisol response is not about eliminating stress. It is about preventing stress from becoming a chronic biological state. Number 3, chronic sleep deprivation and glymphatic failure. The third cause of accelerated brain shrinkage connects directly to something we explored in our sleep video. But here we are going to look specifically at the structural brain volume consequences of chronic sleep deprivation and why they are so direct, so measurable, and so significant in people over 50. The glymphatic system, the brain's overnight waste-clearing mechanism, is almost exclusively active during deep, slow-wave sleep. During this stage, the spaces between brain cells expand significantly, and cerebrospinal fluid is pumped through the brain tissue, flushing out the metabolic waste products that accumulate during waking neural activity. Among the most critical of these waste products are amyloid beta and tau proteins, the same proteins that form the plaques and tangles found in Alzheimer's disease. In a person with healthy, adequate deep sleep, the glymphatic system runs efficiently every night and keeps these proteins cleared to safe levels. In a person with chronic sleep deprivation or poor sleep quality, both of which become increasingly common after 50, the glymphatic system is repeatedly underactivated, waste clearance is incomplete, and amyloid beta and tau begin to accumulate in brain tissue. This accumulation is not merely a future dementia risk. It is an active, ongoing source of brain damage that contributes to neuronal death and brain volume loss in real time. Amyloid plaques are not inert deposits. They trigger local inflammatory responses, disrupt synaptic communication between neurons, and impair the metabolic function of the cells around them. As neurons are damaged and die in regions where amyloid has accumulated, those regions lose volume. The brain physically shrinks in the areas where glymphatic failure has been most pronounced and most prolonged. Research has now documented that even 1 week of sleep restriction to 6 hours per night produces measurable increases in cerebrospinal fluid amyloid beta levels. After years of inadequate sleep, the accumulation in brain tissue becomes structural. Studies tracking brain volume changes over time have shown that adults who consistently sleep fewer than 6 hours per night have significantly faster rates of brain volume loss than those sleeping 7 to 9 hours, with the most pronounced differences in the frontal lobes and hippocampus. These are not small statistical differences. They represent years of accelerated aging compressed into a shorter time frame, driven not by genetics or fate, but by a sleep pattern that can, in many cases, be identified, assessed, and improved. Sleep apnea, as we discussed in detail previously, amplifies this damage dramatically by fragmenting deep sleep night after night while the person remains completely unaware. The repeated oxygen drops and microarousals of sleep apnea prevent the brain from reaching or sustaining the slow-wave stages where glymphatic activity peaks. The result is a person who spends sufficient time in bed, but whose glymphatic system barely runs, and whose brain is accumulating waste proteins at an accelerated rate with every passing night. Cause number 4, chronic alcohol consumption. The fourth cause is one that many people over 50 have not connected to brain shrinkage in the specific, direct way that research has documented. Because alcohol is so normalized in social life that its neurotoxic effects rarely receive the direct, honest attention they deserve. Alcohol is directly toxic to neurons. Ethanol, the alcohol in alcoholic beverages, crosses the blood-brain barrier freely and affects the brain at the cellular level through several mechanisms. It disrupts the balance between the brain's primary excitatory and inhibitory signaling systems. It interferes with the function of neurotransmitter receptors, and it promotes oxidative stress in brain tissue, generating unstable molecules that damage cell membranes, disrupt mitochondrial function in neurons, and contribute to cellular death. The most clinically significant finding in research on alcohol and brain volume is the dose-response relationship, meaning that greater alcohol consumption correlates directly with greater brain shrinkage, and this relationship is present not just in people with alcohol use disorder, but across the full spectrum of consumption, including what is commonly described as moderate drinking. Research tracking brain volume over time has shown measurable differences in white matter integrity and total brain volume between people who drink regularly at moderate levels and those who do not drink, even after controlling for age, education, smoking, and other health variables. The frontal lobes, responsible for executive function, judgment, and working memory, and the hippocampus show the most consistent and most significant volume reductions associated with regular alcohol consumption. Alcohol also disrupts sleep architecture in ways that compound its direct neurotoxic effects. While alcohol is well known to help people fall asleep, it suppresses REM sleep significantly during the first half of the night and disrupts sleep architecture throughout, reducing the deep, slow-wave sleep that the glymphatic system depends on. A person who drinks in the evening may fall asleep easily, but will spend significantly less of the night in the restorative stages, where brain cleaning and neural repair occur. The combination of direct neuronal toxicity and glymphatic disruption makes regular evening alcohol consumption one of the more damaging habits available for the aging brain, even at amounts that most people would consider socially normal. Before today, did you know that chronic high blood pressure, stress, poor sleep, and regular alcohol use were all causing the brain to physically shrink, measurably, structurally, and in many cases, silently? Drop a yes or no in the comments. This level of specificity surprises almost everyone who encounters it for the first time. Cause number 5, physical inactivity and the loss of BDNF. The fifth cause brings us to perhaps the most empowering piece of information in this entire video, because understanding it reveals that one of the most direct interventions available for protecting brain volume is also one of the most accessible, most affordable, and most immediately actionable things a person over 50 can do. Physical inactivity. A sedentary lifestyle with little consistent movement accelerates brain shrinkage through the loss of the brain's most essential maintenance signal. When a person engages in aerobic exercise, contracting muscles release a cascade of molecules into the bloodstream, including BDNF, brain-derived neurotrophic factor, that travel to the brain and directly stimulate the survival of existing neurons, the formation of new synaptic connections, and neurogenesis in the hippocampus. BDNF is sometimes described as fertilizer for the brain, a compound that the brain requires for growth, maintenance, and the structural resilience that protects against shrinkage. A sedentary lifestyle chronically deprives the brain of this signal. Without regular physical activity, BDNF levels fall. Neurogenesis in the hippocampus slows. The formation of new synaptic connections is reduced. The brain's capacity to compensate for age-related changes, its neuroplasticity, diminishes. And without that compensatory capacity, every other cause of brain shrinkage on this list hits harder and produces consequences faster. Research using brain imaging has produced some of the most striking and most hopeful findings in all of neuroscience in this area. Adults over 60 who engage in regular aerobic exercise have measurably larger hippocampal volumes than sedentary adults of the same age. In controlled studies, where previously sedentary older adults began a walking program, hippocampal volume increased by approximately 2% over 1 year, a finding that represents the reversal of 1 to 2 years of age-related shrinkage. Cognitive performance on memory tests improved in parallel with the structural changes. The brain grew. Physically, measurably, in direct response to movement. The threshold for this benefit is not intimidating. 150 minutes of moderate aerobic activity per week, 30 minutes of brisk walking 5 days a week, is the level at which research consistently documents significant cognitive and structural brain benefits. Not marathon training. Not high-intensity intervals, not gym membership. A consistent, moderate walking habit produces measurable BDNF increases, measurable hippocampal volume protection, measurable improvements in processing speed and memory performance, and measurable reductions in the inflammatory markers that drive neuroinflammation. Every walk is doing something real inside the brain. That is not a motivational statement. It is a documented biological fact. The brain retains the ability to grow new neurons, build new connections, and increase in volume in response to regular aerobic movement well into the 70s and beyond. This is one of the most consistently replicated findings in modern neuroscience. Movement is not just good for the body, it is medicine for the brain, and it is available to almost everyone starting today. Before we close, I want to hear from you. Out of these 5 causes, high blood pressure, chronic stress, poor sleep, alcohol, and physical inactivity, which one surprised you most today? Which one made you think about something you have been letting go unaddressed? Drop it in the comments below. And if someone in your life is over 50 and has been noticing changes in their memory or mental sharpness, please share this video with them. The most valuable time to act on this information is before the decline feels serious, That is what sharing is for. Take good care of yourself. Stay curious, stay moving, and I will see you in the next one.